All right, so hopefully you found some different ways that you were not able to estimate this or make an inversion. This X transpose X inverse was not invertible. And so, well, maybe I just gave it away, but the reason why this equation is not estimable, the problem is going to arise when you can't invert X transpose X. So when you can't take the inverse of X transpose X. And there are two ways that that can happen. The first is that P is greater than N. So if you have more columns than you do rows in your data, so if P is greater than N, then you're not going to be able to invert this matrix. And so if you only had 2 observations, but you were trying to fit 3 parameters, not possible. So that's going to be the first way that you wouldn't be able to invert it. So maybe some of you found that out. If you tried to make a matrix that had more columns than rows, it would not be invertible. The second way is multicollinearity. And so what that means is that the columns are perfectly correlated with each other. So if they're linear combinations of each other. So if one column is a perfect linear combination of the other, then you're not going to be able to invert that matrix. So a guaranteed way to check whether a square matrix is not invertible is to check whether the determinant is equal to 0. So let's talk about what the determinant is. Okay, so here I've got this matrix here, X. What is N here and what is P? So N is going to be 2 and P is going to be 1, 2, 3, 4. So based on the previous slide, we know that we might have a problem here. If I tried to take the inverse of X transpose X, is that going to be invertible? It is not, because we're in this N is less than P range. So I can try this in R. I'm just going to build this matrix, this design matrix here. And I'm going to try to take the determinant. The DET function is going to let me take the determinant, and I'm going to take the determinant of X transpose X. And it turns out that determinant is 0, which tells me this is not invertible. Let's try another one. So here's another matrix, X. Do you think that this is going to be invertible? I'm going to give you a second to just look at this matrix. So what is N and what is P here? N is 4 and P is 3, so we're still okay in that realm. We don't have more variables than we do observations, so that's not the problem. But what about multicollinearity? When I take the determinant of this matrix, I end up getting 0 again. And that's because if you take the correlation between the second and third row, they're perfectly correlated, or the second and third column rather, they're perfectly correlated. And you can see why that is, because the second column is just a linear combination of the first, in that it's just the first column multiplied by 2. So if I take 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10, 2 times 2 is 4. And so because there's no added information by this column of x's here, it's not possible to invert this matrix. The determinant is 0, the correlation is perfect between these variables, and X transpose X is not invertible. And so this problem means that if this were our data that we got and we tried to fit a linear regression model, we would not be able to do it. We wouldn't get an answer. So what's a surefire way to tell whether X transpose X will be invertible? Take the determinant. That is the best thing that you can do to check and see if you're going to be able to invert the matrix. Okay, so how do we do that? In matrix form, when we kind of, these bars on either side of a matrix, it sort of looks like an absolute value. That means the determinant of a matrix A. So for a 2 by 2 matrix, this is going to be equal to A times D minus B times C. So basically the multiplication of the diagonal and the off diagonal subtracted from each other. That's the determinant. For a 3 by 3 matrix, it's going to be A times E times I times F times H minus B times D times I times F times G plus C times D times H minus E times G. So just kind of make sure you sort of internalize this. There's a bit of a pattern here that you can kind of recognize in how this works, because essentially It's similar, when you're in the 2 by 2 space, it's just the diagonals multiplied by each other. When you're in the 3 by 3 space, you're going, if you look at the top, we're going across the top values, and then we're taking diagonals on the remaining pieces here. And so first you multiply A by the determinant of the portion of the matrix that are not in A's rows and columns. So if we're going to take A, and then we're going to cross out the row and column, and we're left with this little 2 by 2 matrix here, and we take the determinant of that. E times I times F times H. We multiply it by A. And then we do the same for B and for C. And so for B, we cross out the column, we cross out the row, and we take the determinant of the remaining pieces. And so that is D, I, F, and G. And then same for C. We have a C, we cross out the row, we cross out the column, and we end up with this little matrix over here, and we take the determinant of that. And then we put these all together in a plus minus plus pattern. And so you could write it like this. You could write it out like A times the determinant of EI, FH, B minus B times the determinant of DI, FG, plus C times the determinant of DH, EG. So I'm not going to have you take the determinant of anything more complicated than a 3 by 3 matrix or a 2 by 2 matrix by hand, but it's good to kind of understand at least how this works. And so what I want you to do is go back to your application exercise, and I want you to calculate the determinant of these two matrices, A and B, and then I want you to tell me whether or not they're invertible. Okay, so go ahead and knit that and send it off to HTML land, and we'll continue this in the next lecture.